So, as I said, when I was a researcher, an industrial researcher, I was asking the industry, how can I help? How can I support? And the first question that they agreed on, the first answer was revegetation, but very close behind what the industrial rep I was talking to need is water treatment. Water treatment for mine impacted water, what's called also by the industry mine contact water, is critical. The active technologies that are being used are working really well and they're cost competitive. But when you think about it, it needs a huge amount of chemicals, labor, buildings and infrastructures to handle those active and well-known technologies. And this is why the industry, the mining industry, we need innovation in water treatment. And this is exactly what Dr. Daria Pogava is doing. So Daria's research is dedicated to the development and evaluation of innovative approaches and technologies for water treatment in the Arctic and subarctic regions. She's a research engineer at Western University and a water quality specialist at Corgeo Services. Daria holds a PhD in environmental and green engineering from Western University. Welcome, Daria.
Thank you, Guillaume, for the introduction, and good morning, everyone. I'm really excited to be here today to share the results and updates on our project. So our team is working on the development and optimization of sustainable water treatment technologies suitable for the Arctic and subarctic regions. And this project is a collaboration between Western Engineering and Corgeo Science Services. Here is the outline for today's talk, and I will start with giving you some background of the project. So when it comes to water purification in the Arctic and subarctic regions, it's important to understand and highlight the challenges that we may face. And those challenges, one of the main ones and the most obvious ones is, of course, extreme cold climate conditions of the north. The subarctic region of our interest is in Yukon. That's a ferromine complex, and many of you know this mine site, where there are a number of environmental issues, including one related to the water. So our team is focusing on the ferromine water samples that have high zinc concentration in it. And by high, I mean when we compare the zinc concentration in the water to the effluent quality guideline. So considering the subarctic region of the interest and the contaminant of concern, our team examined different methods that can be used to effectively treat the water, and we came up with a solution of cryopurification that you may wonder what it is. So cryopurification is a process that relies on the physics of water freezing. And the process is nature-inspired because we can take the advantage of the cold climate conditions of the north, meaning that the process can be energy efficient. And because the process relies on the physics of water freezing, we don't use any chemicals, and that means that the process is sustainable and environmentally friendly. But the question is, like, when we freeze the water, we can obtain the pure ice and the more concentrated solution. What to do with the more concentrated solution, because we don't want to just expose it to the environment. So is it good or not? Of course, this is something that needs to be considered, and our team is thinking about, we're thinking about what can be done with this concentrated solution, so-called brine. And the approach that we also tested was the microbial fuel cell process. And we did it through a combination of cryopurification and this process to treat the water and to treat the brine. So considering all of this, I would like to highlight the main direction of this research project and the main objective. For us is this to develop and test the approach that combines cryopurification and microbial fuel cell to effectively treat the water and reduce zinc concentration close to the effluent quality standard. So what we did? So our project progressed through 3 main stages up to now, starting from the lab scale, then bench scale, and pilot scale. So let's first focus on the first 2, the lab scale and bench scale. So both of the laboratory setups, we had of the reactors and the circulating chiller that we can use to produce different freezing temperatures. And these two stages were done to provide us with a scientific foundation of the process and also to prove the concept that this process working for our purposes. By scientific foundation, I mean is to identify the parameters that influence the most the purification process. And through the testing of the reactors, we were able to highlight the main and secondary parameters. So the main ones were freezing temperature, ice front propagation, initial contaminant concentration, and the mixing. So combining all of these parameters, we can obtain the highest removal efficiency. And that was done once again through the testing. We were able to achieve up to 95% zinc removal from the water. What we also did, we developed a mathematical model to validate the process and test this model under different initial and boundary conditions, and that was done for the optimizational purposes. So with all of this, we were able to come up with a foundation to upscale the reactor to the pilot scale. And this is what was done during this winter on site in Whitehorse, Yukon. And you can see we progressed from 170 milliliter system to 130 liter system. So pilot scale testing was done by our crew team. You can see on a picture A this winter, and on the picture B here the pilot scale reactor that was developed and tested based on the results that we obtained through the lab scale and bench scale stages. And that was the initial testing of this reactor during this winter, and the results showed us that the reactor can work successfully and treat the water where we can get up to 98% of contaminant removal. That means we were able to achieve our objective. So in conclusion, I would like to highlight that this process works successfully under the cold climate conditions of the Yukon. Cryopurification can be effectively integrated with the microbial fuel cell process. And this all, what we achieved so far, gave us a foundation for the next stages within the work. And I would like to focus on those. So first of all, we plan to do the iterations and improvements to the pilot scale reactor to have additional testing of this reactor in the upcoming winters in Whitehorse. We plan to add the machine learning to the system in order to optimize the process. One of the exciting stages within the future work is the pilot scale testing at the Minto mine, thanks for the support from the Salt Creek Copper to host the testing. And another step within the future work is to commercialize this process. The project received an interest from the media and was covered in the news. And the results of this project were published in the peer-reviewed scientific journals. So with this, I would like to thank my colleagues from Corgeo. Some of them are here today. Thank you. My colleagues from Western University and LC Design. And I would like to thank MITAX, NSERC, and IRAP for the financial support for this project. Thank you, and look forward for your questions.
Any questions? Oh, so I see a question over here.
Thanks, Guillaume. Yeah, just a question on, so obviously your technology is utilizing the ambient cold temperatures to freeze the water and extract the pure water.
Right.
Is there any idea of what the power requirements would be on a larger scale, or I guess that's something that you'll be investigating in future studies?
This is something that we will investigate in the future studies, but for the example, for the pilot testing, we just use the cold climate conditions. No power was generated like to freeze the water. So that's one of the advantages of the technology because it's energy efficient.
Yeah, that's excellent. Thank you.
Thank you.
Question over there. Yeah, sorry.
Your focus was on zinc removal, but did you have any other significant findings for removal for other parameters?
Yes, we did. We're testing for the sulfides removal and a number of different parameters, including selenium. Yes, and for example, for selenium, we tested the cryopurification, and the water samples were taken from the Wolverine mine.
Okay. What was the removal efficiency for selenium, if you have it on hand?
Similar to zinc removal, up to 90%. No.
Wow, that's great.
Thank you.
I see, yeah.
Thank you for the presentation. I was just curious, a couple points on the text. You mentioned the freezing front propagation impacting the efficiency.
Right.
Can you expand on that, please?
Sure. By this, I mean this is the direction from where we freeze our reactors. So if it's from the top or from the walls, and what we found that when we freeze our water from the top, that gives us the highest removal efficiency because of the natural convections involved in the system. So that's why it is affecting the efficiency. But also, that's one of the interesting experiments that we did. We freeze not only from the top and from the walls, we freeze from the walls, from the bottom, only from the bottom. So that was all done to find what will be the best and what can give us the highest removal zinc.
Thanks, Daria. I have a question for you. You showed that you had 90 to 98% removal, which is fantastic. My question is that one cycle? Can you repeat this process for multiple cycles? So is this an iterative process, or how can that be improved?
Thank you, Yuri. Yes, that's a repetitive process. You can do a few cycles. So 90 to 98, that's one cycle of freezing. And that can be, we can do another cycle if we want to. Depends on the goals. Also, like when it comes to the brine treatment, we propose the microbial fuel cell, but at the same time, we can also do another round of freezing.
Hi, Daria. Thank you for the presentation. I just wondered, have you, it looked like it was still kind of a small scale at the moment. So have you been able to start considering any of the operational kind of application technologies or techniques that you'll be able to use? Or is that for future studies as well?
That is for future studies. So right now, we finished the initial round of testing of the pilot scale reactor. So we plan to modify the reactor first and do another round of testing. And after that, based on the results, we will be thinking about upscaling.
Thank you all. Oh, there is another question here.
I suppose this works because as you start, you have a phase separation, right? So you're concentrating the pure water in the ice, and then you get with the zinc sulfate brine. But as you get the brine, you can also start precipitating because you're supersaturating mineral phases, and now you have another solid phase mineral precipitates to deal with. I was wondering if that came up as an issue, and if you need to think about how to handle it if it has.
An issue of precipitation?
Yeah, precipitation of minerals that are supersaturated in the residual zinc sulfate solution.
Yeah, I understand, but we haven't had this issue in our testings.
Thanks.
Thank you. All very good questions. Lots of questions. Thank you very much, Daria. Just to conclude, I was very happy to see that you advanced to the pilot scale. Again, sharing my experience from the last 10 years working with the industry, they always want, and the regulators as well, they always want to see some pilot scale as a demonstration phase between the lab and the real world. So having some interest from Selkirk Copper to host a pilot scale on site is very exciting for the future. So thank you very much for your presentation.
Thank you, Guillaume.